In this video, we'll study the so-called Simplex Method for solving linear programming problems. Recall that the general linear programming problem is a problem of trying to maximize or minimize some objective function subject to a system of linear inequalities. The way that we solved it in the past, the graphical method, was to actually draw this region out, the region that satisfies all of the inequalities simultaneously. This was called the feasible region. And we only needed to consider the corner points of this feasible region because due to the corner point theorem, we know that the variables that lead to a maximum or a minimum are on these corner points, right? They're going to be only at these corner points. And so we just needed to look at all the corner points and determine which corner point led to the biggest or the smallest of the objective function. Okay? And that was easy to do in 2 dimensions with only 2 variables because we could easily draw the region in 2-dimensional plane, or 2-dimensional space. The problem is if we have more than 2 variables, and we can certainly think of linear programming problems that have more than 2 variables, we become stuck. We can't really draw it. In fact, it becomes impossible if it's anything bigger than 3. And even in 3 dimensions, it becomes very difficult to see what's going on. And so there's actually a nice algorithm that leads to a solution to a linear programming problem, which is called the Simplex Method. Okay? And it works for any dimensions at all. Okay? It's very nice to use. And so anytime we're working with dimensions higher than 2, in other words, we have more than 2 variables, we want to revert to the Simplex Method. It's a very nice algorithm for actually figuring out and solving linear programming problems. Now, since we have more than 2 variables, it's very convenient to change the notation of these variables. Okay? Instead of labeling each one of these variables as some separate letter like x, y, z, it's better to actually label the variables with subscripts. Okay? So and I've listed some variables here. So from now on, when we're dealing with the Simplex Method, we'll label our variables with subscripts. So x1, x2, x3, and so on. Okay? And that's a much easier way of keeping track of everything. In general, we're dealing with a system that has more than 2 variables. So the region that satisfies all of the linear inequalities with more than 2 variables forms some kind of polytope as a feasible region. A polytope could be something in higher dimensional space. I've taken something here and smashed it into 2 dimensions, but in general it could be much higher dimensions as well. Just to give us an idea of what's really happening underneath the surface of this algorithm, I just want to show you exactly what's happening, at least in a geometric picture, okay? Even though we can't really draw the proper picture. So here's my feasible region, which is some kind of higher dimensional shape. And each one of these points are the corner points, okay? My corresponding corner points. The algorithm called the Simplex Method works the following way. We identify one of the corner points, okay? So there's going to be some way to identify one of the corner points. And what we do in this algorithm is simply step from one corner point to the next corner point to the next corner point. And all we've got to do is look at our objective function and determine whether or not it's the biggest or the smallest each time. Okay? And that's really all that we're doing for this Simplex Method. That's what the algorithm is doing. So we're starting with one corner point and we're moving to the next corner point, then to the next corner point, and finally we reach our maximum or minimum. Okay? And it's going to be in some kind of higher dimensional space that we can't really properly draw. I just wanted to give you some kind of geometric picture of what's really happening underneath the surface of this algorithm called the Simplex Method. Before we talk about the specifics of the algorithm itself, we have to introduce what's called a slack variable, okay? Or slack variables. And a slack variable is just like it sounds. We're just sort of picking up the slack in some sense. So if we have some kind of inequality, right, where a and b are just real numbers, here's some kind of inequality, and I make it an equality by adding this y, which is a positive number, a positive real number, then y is called the slack variable. It picks up the slack. So in other words, it's just a variable that makes an inequality an equality. That's it. Okay? So it makes this inequality an equality. And that's what we call a slack variable in general. And slack variables will be very useful and an integral part of the actual algorithm we'll come up with that's called the Simplex Method. Probably the best way to develop this algorithm, the Simplex Method, is to look at an example. So consider a standard linear programming problem, except this time we have 3 variables. Okay? So I want to maximize this objective function, which is just, of course, a linear combination of 3 variables, x1, x2, and x3, subject to the following constraints, okay? Which are just 2 inequalities here. And of course, we have the other further constraint that each one of the variables must be positive. Okay? And so this is just like the linear programming problem we've talked about before, except I have 3 variables. And so the solution, instead of an ordered pair, is going to be an ordered triple, x1, x2, and x3. Okay, so the solution is this ordered triple, x1, x2, and x3. And it's going to be some ordered triple that, in fact, maximizes this function. Okay? It's a function of all 3 of these variables, x1, x2, and x3. So the first process in this algorithm is to rewrite each one of these constraints and this objective function in a different way. So the first thing I'm going to do is take these 2 constraints, these 2 inequalities, and turn them into equalities by adding slack variables. Okay? I'll call the slack variables S1 and S2 for slack 1 and slack 2. It doesn't really matter what you call them. I'll just call them S1 and S2. Again, all that matters is that they're non-negative variables. So I'll take the first inequality. I've got x1 plus x2 plus x3. And I'm going to add slack variable S1. Okay, it's just some kind of non-negative variable that makes this equal to 100. So now it's an equality. The other inequality, we've got 10x1 plus 4x2 plus 7x3. Now plus S2 for slack variable 2, which makes this an equality equal to 500. Okay, notice all I've done is I've just added S1 and S2 to make each one of these inequalities, these constraints, some kind of equality, another kind of constraint, with S1 and S2 being the slack variables. The other thing that I want to do is I want to rewrite this objective function with these parts of the equation on the other side. So z is positive, and I want to put all these on the other side. Okay, I want to make z positive. So when I take this 120 and I bring it to the other side of the equation, I get minus 120, right? So I get minus 120x1, minus 40x2, minus 60x3, plus z is equal to 0. Okay, so I took all of these things on this side of the equation, brought it to the other side of the equation. Z is positive, and I'll have a 0 over here. Okay, and that's what I've written down here. So I've simply rewritten this entire problem and all of the constraints, including the actual objective function, in a different way. They're all equations. Okay, so you really have 3 different equations right here.